Hello and good day to everyone. So we are the group 1 and we are here to discuss the logical equivalences, predicates, and quantifiers in the propositional logic. And today I will discuss the commutative laws in the logical equivalences. So what is the commutative laws? According to this law, if we combine two statements with the symbol and or, then the resultant statement will be the same, even if we change the position of the statements. Meaning, if we have the statement P and we connect it with the symbol and or, and the statement Q, even if we change it in both ways, they are still the same in meaning, and in equivalence, they are still the same. Next, we have the negation laws. So, the negation of a conjunction, logical and, of two statements is logically equivalent to the disjunction, logical or, of each statement's negation.
In proposition logic, double negation is the theorem that if a statement is true, it does not mean that statement is not true. This means that this proposition A is not logically equivalent or expressed by the expression. Here, the symbol represents equivalence and the symbol represents negation. So, we have to check if these statements are logically equivalent. We have what's so-called double negative property, so the way to do that is you to make a truth table on each side, and you have to make sure that they have the exact same truth value in each row. So let's start by writing down the truth values for P. So P can be true or it can be false, so that takes care of the right hand side. That's our truth table for P right there. Now, we need to come up with the left hand side. So, we can start by looking at not P. So, not P is the negation of P. So, it has the opposite truth value. So, here, it will become false, and here it will become true. Then, we can look at not P. That's the negation of not P. So, in this case, it's false. So, it becomes true, and in this case, it's true, so it becomes false. And so, now to check to see if these are logically equivalent, what we do is we look at the end result. So, look here and look here, row by row. These are exactly true, true, false, false. So yes, these are logically equivalent.
Good morning everyone. So today I'm going to give one of the examples of proving using the logical equivalences. So here is the example. Show that negation of P or negation of P and Q and negation of P and negation of Q are logically equivalent by developing a series of logical equivalences. So if you didn't know yet the logical equivalences, so this is the logical equivalences. We have to write, so first we have to write the original form and start applying the logical equivalences. So first, we have to use the second De Morgan's law, and it will become negation of P and negation of quantity, negation P and Q. Second, by the use of first De Morgan's law, it will become negation of P and quantity of negation of negation P or negation Q. Negation of Q. And third step, by the use of double negation law, it will become negation of P and quantity of P or negation Q. Fourth step, by the use of distributive law, it will become negation of P and P, or negation of P and negation of Q. So since according to negation law, negation of P and P is logically equivalent to false. That is the reason it is replaced by F. So it becomes F, or negation of P and negation of Q. And by the use of cumulative law for disjunction, it can simply write as negation of P and negation of Q, or F. And by the use of identity laws, P or F is logically equivalent to P. That is the reason why it becomes negation of P and negation of Q. Therefore, negation of P or negation of P and Q are logically equivalent to negation of P and negation of Q.
Good day, everyone. Our topic is all about propositional equivalences, predicate, and quantifiers, including predicate. So, predicate. It is a sentence that contains finite numbers of variables, or it becomes a proposition when specific values are substituted for the variable. So, for example, x is greater than 3. So, our subject is x and our predicate is greater than 3. We can denote this statement x is greater than 3 by propositional function, or px. So let's have another example. So let p of x denote the statement x is greater than 3. What are the truth values of p of 4 and p of 2? So the solution are, we can obtain that statement p of 4 by setting x is equal to 4 in the statement x is greater than 3. So as we can see, 4 is greater than 3. So the statement number 1 is true because 4 is greater than 3. So let us proceed to the statement number 2, the p of 2. So let the value of x substitute to 2. So we have 2 is greater than 3. As we can see, 2 is not greater than 3. So it means the truth value of statement number 2 is false because 2 is not greater than 3. So that's all the procedure of predicate in the propositional equivalences, predicate, and quantifiers.
Good day, everyone. In this lesson, we will discuss the logical equivalences involving quantifiers. So first, let us define what is quantifiers. Quantifiers are words that refer to quantities such as sum, meaning, all, and indicate how frequently a certain statement is true. So we have two types of quantifier. First, we have universal quantifier, and the second is existential quantifier. So what is universal quantifier? The phrase for all is called universal quantifier. It is denoted by this symbol. This symbol represents for all, for every, and for each. For existential quantifier, the phrase there exists is called existential quantifier. It is denoted by this symbol. This symbol represents there exists an x, there is an x, and there is at least one x. So this is the example of universal quantifier. Let p of x be the statement x plus 1 is greater than x. What is the truth value of the quantification for all of x, p of x, where the domains consist of all real numbers? So when we say all real numbers, we can use here 1, 2, 3, 4, and so on. So the statements say that x plus 1 is greater than x. So for instance, we will use number 2 to substitute the value of x. So 2 plus 1 is greater than x. So, x here is, so 2 plus 1 is 3. So, as we can see, so 3 is greater than 2. So, as we can see that the statements are true because 3 is greater than 2.